With that, I'm very pleased to introduce a longtime friend and colleague, John Fonner, who is celebrating his 1-year anniversary, or Googleversary as we call it, here at Google Cloud today. He is in my team also as a product manager at Google Cloud, and he's here to talk about high performance computing on Google TPUs. Thanks, John. John, you're on mute.
Just sharing a window. Hi, everyone. I am on the tail end of a cold, so I apologize for any audio issues. I may sip some water as we go along, but I brought the coolest background wallpaper in the Austin office here at Google and all my enthusiasm to talk about TPUs with you today and how we're using them to do things that are not specifically AI. So before I get started, I want to acknowledge I have the honor to represent work that is really from a whole team of people. And I wanted to call out 3 specifically who have contributed a lot to the technical piece behind this work. That's Yifan Chen, Xinshu Zhang, and Jin Guan. They're all in Google Research. They're in the same group together. They're amazing people to work with. It's one of the perks of being at Google to be able to collaborate and work alongside really talented individuals like these 3. So I wanted to start there and just preemptively thank them for all that they've done for this and recognize that this takes a whole team to build these types of things. So I get to talk about 4 things. I'll try not to rush too fast. I have plenty to cover. We'll talk about the TPU architecture, focusing really on one TPU at first, and then how they network together so that we can get many TPUs acting as a unit. We'll look specifically at precision. This is a very big topic in high-performance computing right now, as a lot of the accelerators that we use, both GPUs and TPUs, are prioritizing lower precision because of the trend for AI utilization. I'll talk about programming and how we get our ideas and code on a TPU. And then we're going to work on a hands-on example that I will share with you all that's on distributed fast Fourier transforms. If you don't know what that is, no worries. I'll give a high-level explanation. But it's an opportunity to see everything come together, to have code that's written, that's running on multiple TPUs, that is solving a problem that is not AI specific. Okay, so TPUs are they're very rapidly developing. The very first TPU was in 2025. Work, I think, started technically in 2013. Sorry, it was in 2015. Work started in 2013. And recently, we've been coming out with new TPUs at an annual cadence. This is around twice as fast as CPU data center SKUs are released, if you're used to following that. So we'll end up using the V5 TPUs today when we get to the hands-on. But you'll notice those are just from 2023. So even though it's several generations back, they're very recent. They're very great to use and highly performant still. You can run today as well Ironwood TPUs on Google Cloud. Those are out and available. They're very powerful. And earlier this year, we've announced the TPU version 8 that's coming online. So I'll try and call out the different versions as we go. Again, everything from probably V4, V5 on is still in very active use within Google Cloud. They're all really amazing chips to use. We'll be using the V5s hands-on. The next sheet, I'm going to look at an Ironwood to talk about architecture, but I'm also going to play you a video that talks about version 8. So there's multiple versions, same underlying architecture as we go forward. So to get going, I'm going to start and let Amin tell us about TPUs in a concise way, better than I can. If you are part of the HPC community, I want to just draw your attention to notice the type of language that Google uses when it talks about its TPUs. It talks about the capabilities of those TPUs. Some of those might be things that you're used to. Some of those might be things that are a little bit different. If, as we go, you have ideas on this, feel free to post that in chat, and we can kind of talk about how TPUs are discussed. All right, here we go.
Models have evolved to keep up with the changing demands, and the infrastructure needs to evolve as well. Recognizing that the infrastructure requirements for pre-training, post-training, and real-time serving have radically diverged, I'm thrilled to announce that Google will be launching 2 8th-generation TPUs, TPU-8T and TPU-8i. The new frontier models will reach trillions of parameters. To build these frontier models of tomorrow, we need infrastructure that can handle mega-scale pre-training without being stalled by data bottlenecks. TPU-8T is optimized to reduce training time for trillion-parameter frontier models, delivering a staggering 121 exaflops of native FP4 computes and 2 petabytes of shared HBM within a single 9,600 chip superpod, a 3x increase in peak performance per superpod over the previous generation. As we enter the agentic era, the industry is hitting what we call the latency wall, where traditional architectures struggle with the real-time demands of autoregressive decoding and complex chain-of-thought reasoning models. That is why, alongside TPU 8T, I am also thrilled to announce a second 8th Gen TPU that directly addresses this issue. TPU 8i is our specialized post-training and inference engine. We are optimizing its core features to be the best reinforcement learning and serving infrastructure for the next generation of reasoning models. A defining breakthrough for TPU 8i lies in its ICI networking architecture, which pioneers the board fly topology for TPUs. By shortening the network diameter needed for all-to-all communication, the very heartbeat of MOE and reasoning models, BoardFly achieves up to a 50% improvement in latency for communication-intensive workloads. Customers often ask if scale must come at the expense of speed. The reality of our 8th generation TPUs is that we have transitioned away from a singular, one-size-fits-all approach. While both architectures remain highly capable across the full AI lifecycle, encompassing pre-training, reinforcement learning, fine-tuning, and serving, we have purposefully optimized each system to unlock maximum efficiency and value for the most critical stages of AI development. These next-gen TPUs will power Google's own AI infrastructure needs to build the best models, like Gemini, and these will also be available for our Google Cloud customers by the end of the year. We can't wait to see what the world will build with the power of TPU 8i and TPU 8t.
All right. So I'm going to check chat now as this goes along. Tell me, what did you hear that he talked about that in terms of performance and capabilities? What would you say makes TPU special based on this? Okay, speed of light, Duval Morgan. I'll send you your check later. Yeah, this is an interesting thing, right? How many TPUs do we want to work together? The SuperPod there is over 9,000 TPUs, which is a lot of TPUs to network together. So you saw that picture of the interconnects and data moving quickly, and we'll talk about topology here in a couple of slides. But the point is, you have to have these physically close together. The speed of light is actually fairly slow. If you think about a processor that is, say, 1 gigahertz, usually processors are a little bit faster. So 1 clock cycle of a 1 gigahertz, CPU, GPU, TPU would be 1 nanosecond, right? Does anyone have a feel or a guess at how long it takes light to travel like 100 meters, like a football field, if you have a football field-sized data center? You can ask Gemini as we go. It should tell you that if you have 1 nanosecond is the clock speed, but if you're trying to send data across a football field, you're actually in a 300 nanosecond range. It's painfully slow if the data center is spread out. So that is the equivalent. If you think of a clock cycle as doing a math problem, let's say you can do a math problem in 30 seconds. It would be like waiting 8 hours to get the message from another core that's a football field away that's scaled up. So that 300 nanoseconds is slow. That's so 300 nanoseconds ago. Exactly. It is forever ago from the perspective of these processors. So these things are very tightly placed. And that's why you look at the background and you see the rack next to rack next to rack. They don't want any extra space between these nodes so that the speed of light has less latency, doesn't have as far to go. And you can keep going and communicate and get all these things to work together and waste as few clock cycles as possible on the networking piece. And I'll actually talk more about how the Systolic array helps us do that with TPUs as well. Other things that could have been noticed, you can talk about the precision. So he said exaflops of FP4 precision. So most TPUs in the matrix multiply unit, they prefer BF16, which has the same range as a 32-bit floating point number, the format is, but much less precision. They can only store values between 0 and 128, plus or minus, but then you get lots of range on the exponent to be able to store things. So they're lower precision. Other things, yeah, the interconnects, we'll talk about that, the number of TPUs that work together, and then there's a lot of memory bandwidth going on as well. So that's kind of how Google talks about it. let's dive into the architecture. So this is a diagram of a V7 TPU. This is the so-called Ironwood TPUs that are the newest ones available on Google Cloud right now. And there's a PCI interconnect over here on the left side that lets the TPU communicate with the host so that you can get movement of data from the host onto the TPU. And it's used for some other things too, I'll talk about on the next slide. This can go onto the interconnects, the fabric that's on the chip itself. There's a bunch of high bandwidth memory shown here at the bottom. There's a bunch of controllers that feed this memory onto the chip. And then we have a few types of cores that are here. There are these sparse cores. These are essentially like data handling cores. They sit very close to the high bandwidth memory. They're intended to essentially do the types of data operations that need to be done to make sure that it can feed this main tensor core that's on the board as much as possible. You'll see, by the way, that Ironwood on one physical chip, it has 2 tensor cores. Some models or versions of TPUs only have 1 tensor core per chip. In fact, even the V8, it's not a downgrade. It's just kind of how you balance the amount of computing to memory bandwidth and how that's packaged on a die. So even the V8 TPUs, you'll see one has 2 cores and one has 1. So when we get to the core itself, the MXU or matrix unit, the matrix multiply unit, is really the workhorse of the tensor core. And those are intended to do, they're made up of, well, it depends on the version, but many thousands of these elements that each do this multiply accumulate operation. And they're connected in a way that I'll show on the next slide that makes them really powerful to work together to solve these huge matrix operations. The other piece here is the VPU, Vector Processing Unit, and that is responsible for doing things, essentially the stuff that's not linear matrix operations. So this does the nonlinear work and exponentiation and sine waves and all those sorts of types of calculations. And also the virtual memory is sitting right here on the die as well. So the VPU can also do things to memory to help set it up for the MXU. These are little logistics chips that are shown here on the top. The other big piece I wanted to show on this architecture is the ICI, and you heard Amin mention that in the video. This is the interconnect that we use for TPUs. And you'll see each of these has 6 different links on the card. Well, that's relevant in the way that the topology of how these are linked together. These are routed, they're serialized and deserialized, and they provide a very low latency. That was another key word from that video. Low latency connections with the other TPUs that are nearby. So that's kind of the big picture of what we're looking at for the architecture that's there. Let me talk about the systolic array. So within the matrix units, the way that these are orchestrated, when doing these matrix operations, it's not required that they all perform the same computation at the same time. Usually, unless you're this bottom left guy here in this image, to be able to do the operation that you want to do, you need the output of your neighbor to the left or the neighbor below you. And so the TPU specifically handles data flow to be 1 clock cycle shifted. This means that data arrives on the first one, it does its computation, and the next 2 elements are fed at exactly the right time with just the data they need in that clock cycle to be able to do their part of the computation. This means that intermediate results are never sent to memory or never stored in some temporary register. They're sent directly to the neighboring component. This is also challenging, you'll notice from the programming side, is that things come out of order. So if you watch at the 5 here, this is like a handwriting, looking at a handwritten number and classifying it as what number it is. You'll see that the data down here for number 6 starts to flow in before the top is done with number 5. So this systolic output also means that your output is kind of coming in pieces and overlapping. This overlapping makes it a little bit more complex. That complexity is handled in software, it's fine. But the thing that it really does well is it keeps the input buffered. It keeps these computing units completely fed so that you're not having any idle cycles, and the TPU can really shine and constantly be performing the computation that we need it to, and it's really nice. So this was a really big part of the system architecture, the TPU, and a big part of the innovation there. Okay, going on. Let's talk about, we've been focused on one TPU. Let's talk about lots of TPU. And Mary, if you have this link, you can put it in chat so people can explore on their own. Let me hop over to what this looks like. Share this tab. So this, we talk about TPUs in slices. So this is 64 TPUs working together in a 4x4x4 topology, physical topology. And what is interesting here is that these TPUs are physically linked together. So we have 4 that are essentially on a board together. In fact, if you saw the video, you see a lot of times there's the big board that's got the 4 TPUs on it. So that's represented by these 4. And if I pick one kind of in the middle, may have to use some imagination. Let's pick this guy here in the middle. You'll see that it's connected to its neighbors, kind of up and down, and there's a left and right and forward and backwards here. There's 6 connections that are being made physically to the TPUs that are near it. This maps to those 6 connections in the ICI. I don't know if you remember the diagram. It has 6 channels that it's able to use. So it's directly connected to its neighbor. And if you see on these boards, there's this extra diagonal connection. And this is actually the PCIe interconnect. So the TPUs are able to use the PCIe to talk both to the host as well as each other within a board. So you get lots of network connections. Google just launched some new GPUs. They talk about NVLink 72, the idea of taking 72 GPUs and chaining them all together. With TPUs, right, this is on the order of 9,000 chips. So the idea is to take this and make it part of a really massive compute engine that can all work on the same problem, all with the lowest latency and the highest bandwidth. Okay, let me come back here. Oh, why is it my, let me do slideshow first, and then come back and share that tab. There we go. This is what I wanted. So that is the topology. That's one TPU we've looked at. That's lots of TPUs working together. Let me talk for a little bit about precision. So this is just a screenshot of an HPC Wire article that was out there. And they're talking, as much of the HPC community is talking about, that when we look at new accelerators, be these GPUs or TPUs, there's a lot of pressure on these chips to move away from FP64 performance. So going from 37 teraflops down to 1.2 teraflops in this case. And TPUs are not trending the other direction. FP32 and emulated 64 performance is fairly flat. When you look down at the lower precisions, then the performance is going up over time. That's true of all accelerators. And the trade-off here is really one of power and capability. So it takes more physical die space to put computing components that can handle FP64 than it does to do FP16 or BF16 or FP8. And so there's pressure on the chip manufacturers to cram more transistors onto their chips. So they're using lower precision math units, and those math units are perfectly acceptable for AI use cases. And AI use cases are driving a lot of the purchasing of these types of accelerators. So this is just sort of the market pressures pushing things toward lower precision. This is really a surprise to the HPC community. Maybe not a surprise. Maybe that's the wrong word. And there have been groups that have been looking at precision and how that affects different HPC use cases for a long time. So credit to all those people. But I'll say this is a new pressure on the HPC community to really look at what type of precision we need when we're doing different scientific applications. Can we handle lower precision? Do we really need FP64? And how do we manage both of those things? If we really need FP64, how do we get it? And if we don't, how do we quantify the trade-offs that we're making? So Satoshi Matsuka, he published a paper in, I think it was April of this year. FP8 is all you need. Very fun title, riffing off the 2017 Google paper of attention is all you need. And he talks that talks about native, what he calls native hardware FP64 performance. And he contrasts this to where we could go with using FP8 tensors and then using software to aggregate operations to still maintain FP64 precision, or not. There's a couple of things. So the idea is that FP8 matrix units can serve as a fundamental primitive, and you shift the complexity from the hardware to the software to be able to accumulate 64-bit precision using FP8 operations. And he essentially says there's going to be some overhead here, that if you have an emulated version of your operation, that you're going to take some number of FP8 operation, native operations, and merge those together in something like an Ozaki scheme. There are already multiple software algorithms that do this, but there's going to be some factor of performance that you're losing versus just doing FP8. And if this factor is less than the trade-off of trying to do it natively on a different chip, then you win in the end. Then you are able to take advantage of the hardware. It just requires this layer of emulation. So I'm not saying that I'm going to present the solution to all of this in this little talk, but it is something that I think about a lot as one who's using TPUs to do computing, and really that I believe the whole HPC community globally should be thinking about as the hardware and the hardware's capabilities kind of moves underneath us, how we adapt. HPC has always done this with hardware, how we adapt. GPUs come on the scene, we figure out how to adopt them and make use of them. TPUs come along, we're doing the same thing with them, and on and on. So if we talk about precision for a second, and this is Shin-Chu in the Google Research Group actually did these numbers for us. So the idea of this table is how many digits are correct if I do a 32-point precision measurement, so sorry, 32-bit precision measurement versus some gold standard, like a NumPy, extra long operation. And she tried it with different types of fundamental math operations and then looked at the number of digits that were correct. Well, an FP32 has a 24-bit mantissa. So of all the bits that are in there, 24 of them are devoted to the number and the rest are devoted to the exponent. And if you think about each bit as being 0, 1, so it's 2, it has 2 options. So the number of numbers that you can represent is 2 to the 24th, which is about 10 million, just under. So this gives us really close to 7 to 8 digits of precision. And what we find is, both unsurprisingly but reassuringly, that if we take a FP32 measurement of various things and test them multiple times and compare them to a gold standard answer, we actually get the full 7 digits of precision. In other words, we're not sacrificing anything more than what we're sacrificing when we talk about how they're represented. And it's also a good reminder that I don't know how often you do math, but there are a whole lot of use cases where you probably don't carry out your numbers beyond 7 digits. 7 digits really is perfectly suitable. And what we get when we do FP64 precision calculations is we get almost 15. It's a 49-bit mantissa. Gives us almost 15 digits of precision, which is fabulous. And in some cases, truly we need this because there's an accumulation of errors, and any small error in that number can build over time. But this sort of looks at this question of how many do we need and what algorithms are we using where we can get away with lower precision. Here's a study done again by Yifan's group in Google Research that was looking at computational fluid dynamics on TPUs. They did this on V3 TPUs. They've done this work again on V7. It's actually very performant, and it's open source, and it's on GitHub. So it's a fun thing to check out. This is code that's written in JAX. JAX is the main way to write code that gets expressed on TPUs and runs. And they're using float32. And they actually did a comparison of looking at specific simulation output, looking at the error rates that they get when they use double precision. This is what we would call FP64 versus single precision. This is FP32. And what they find is that the error that you are getting in your fluid dynamics is dependent on the time step that you're using as you're doing this work, as well as the grid spacing. And if you choose really bad grid spacings, then no amount of precision is going to compensate for the errors that you get. But if you're doing a good job, the errors are very low. And it turns out, even when you cut the precision in half, as long as you're doing a good job with your time step and your grid spacing, you can still maintain extremely low precision. Sorry, extremely high precision, extremely low error, even when you're going with single precision as opposed to double. So frankly, this is encouraging. This only gets us from 64 to 32. But even if we start using Ozaki scheme to come back to 32, we're finding some real interesting HPC use cases, kind of with this sweet spot in the middle, where TPUs can really show advantage, and really all the types of accelerators that are shifting toward lower precision can perform well. Okay, so I talked about JAX. We're going to see some JAX later on if I don't use up all my time. JAX is interpreted by what we call XLA. And this is the compiler stack that is there that runs on TPUs. JAX is the Google flavor and set of libraries that are used to run code on TPUs. There's also PyTorch that many of you, I'm sure, have heard of. This is the more popular library right now for doing machine learning and just a lot of different things. XLA accepts really all of these. There's a team here at Google that makes sure we have great support for PyTorch. XLA will compile this, and it's actually generic. So XLA will compile for GPUs, CPUs, both x86 and ARM, and it can target TPUs. So this is the primary way that we get code and express it onto TPUs. There are some formats that OpenXLA will also take in that are kind of the optimized kind of internal representation or pre-compiled version of this code. So stable HLO is one format. PJRT is another. There are some fun little tricks where you can, take any other thing and emit stable HLO as your output, and then still use the XLA compiler stack to go run your code on TPUs. So that's a very fun space to look at. You don't necessarily have to use any of these languages if you can just emit stable HLO. And then Palace is the other thing I wanted to point out. So HLO is a high-level optimization. That's what it stands for. There's really two layers of optimization that XLA does when it's taking code and prepping it to go run on a TPU. A lot of these gymnastics, by the way, is trying to put the intelligence in the compiler, because I talked about systolic array. There's this idea of double buffering the memory to make sure that data is constantly flowing into those TPU tensor cores to keep the compute units busy, and the compiler does some extra work to handle that last mile complexity of the systolic array and those tensor cores. So there's a high-level optimization. There's also a low-level optimization underneath that. And if you are very hands-on, or you have a very performance-sensitive piece of code, one of the ways that Google handles that is this Palace dialect that will actually bypass the high-level optimization, and it does a lot of the memory allocation and handling manually within the code to give the developer more control, and then it only goes through that low-level optimization pass before it runs on TPUs. So I wanted to call that out. The documentation is excellent, really, for all of this. Also on this, maybe I'll show it here in a second. One of these pages also has a comparison of all the TPU generations, so it's a lot of fun to see these things kind of laid out. There's a lot of information out there. Okay, let me get on to our hands-on piece. I think I've got just enough time to do this. So I'm going to show you a distributed fast Fourier transform. Let me make sure we're on the same page for what this is doing. So a Fourier transform, the idea is that a lot of times we collect maybe something like this purple signal at the bottom. Maybe an earthquake, or we're looking at frequencies coming from space, or an MRI image, or we're looking at forces in molecular dynamics. There are a whole lot of things that look like this. What we can do is say that for any shape that we see, this is made up of some underlying components, some fundamental frequencies that are expressed here at different amplitudes. So for example, this funny shape here on the bottom is actually just adding these two signals together, a 15 hertz wave and a 5 hertz wave together, and you get this funny shape. This can look very confusing, but there's this mathematical tool, Fourier transform, that lets us take this time domain data and convert it into frequency domains. So our x-axis is no longer time, but it's frequency. And each of these kind of contributing frequencies that go into it come out as peaks. So here's one at 5 hertz and here's one at 15 hertz in this example. Beyond just the Fourier transform, there is a really clever implementation that is credited to Cooley-Tukey from 1965. Ironically, of course, Gauss actually figured this out. He just never thought to publish it back in 1805. But it's a really neat way where you take the data and you take every other data point, the evens and the odds, and you separate them. And what it does is it essentially takes advantage of harmonics. So if you have a wave that's double the frequency of the last one, then the peaks and valleys actually overlap. One just makes 2 trips up and down, while the other one makes 1 trip up and down. But if you solve the values at those points, it's the same answer. So rather than calculating it twice, it takes advantage of these harmonics and does this all in a very, very efficient way. And by the way, just to point out, this is discrete data, lovingly called DFT, unless you do quantum work and DFT means something else. But there's a whole lot of use cases. It becomes awkward to try and enumerate them because there's so many that use discrete fast Fourier transforms as their core. So we will be doing, and actually this paper here is large-scale discrete Fourier transform on the TPUs. This is a distributed fast Fourier transform that I have in a hands-on session. I think Mary's going to post links to these in the chat. This is something that you can follow along with, and I'm going to walk through it fairly quickly because I only have a few minutes. Give me just a second. Okay. So one of those links is going to point you to a GitHub page. Again, this is Google Research. We have a TPU, a high performance computing repository. You've got to go a couple of levels deep under notebooks, presentations. This is the only one there for now. Hopefully this grows over time. This is a IPython notebook format that has the whole lab in here. It's very well documented and is meant to be walked through self-paced. So I'm going to cover this a little bit right now. I'm going to run out of time, but this is something that you can utilize on your own. And you can run this by going to the other link that Mary should have posted, which is Google Colab. One of the options there for loading a notebook is to import from GitHub. So you can simply point it to this URL and it will pull this in. And when you're all done, it's going to look very slightly different from what I have here. I'm running this notebook on 8 TPU cores, but you will see this. And it has all of the different documentation pieces interwoven, just to kind of cover what you'll learn. What is JAX? What is a distributed FFT? Again, it's embarrassing to talk about the use cases. It's like a whole lot of things that we rely on day to day are running here. And we'll go through. So I have hidden most of the code. Inside here, there's a lot of code that Shinshu and Jen and others have written that do a nice job of encapsulating this. But the way that Jupyter Notebooks work is for each one of these, you'll hit Shift Return, it'll execute it, and then we get output that's below. So I get a warning message, but then I am told that I am on a TPU back end that has 8 devices and it enumerates them out. If you open this up in Colab yourself, even on the free tier, you can go up and there will be a button up here on the top right. You can connect to a TPU backend and run this on a TPU, which is a really fun way to both see this in action and if you want to try things out on a single TPU core. So let me just kind of run through. There's going to be a few things that we can do. I'll go ahead and run these. You can compare the performance of a TPU on doing just matrix operations to a CPU. Here I show a speed up of 17.3x. This is actually a really beefy CPU that's on this node. but the TPU just eats matrix operations for breakfast. And it's much faster than the CPU at doing these types of things. We can do a similar comparison of looking at FFTs specifically on a TPU versus a CPU as just a single TPU. The image I showed was a 1D fast Fourier transform, by the way. You can do this with 2D for like image compression. You can do this with 3D. Most of this is actually using a 3-dimensional array and doing fast Fourier transforms on it. But again, you can look at when we start to do this with lots of data and it's given a little bit of time, the TPU really shines. We are going 67.5 times faster. This is always a little bit different. And you'll see that we're using 32-bit precision here, so we're getting 7 digits that are correct. The error is to the -7 power. And then when we start to look at multiple TPUs, this is called time decimation, where the time data is split up across, in one dimension, is split up across the number of TPUs that are available. If you're just doing the single TPU free tier, you won't be able to see the speed up here. You can still run it, but you can, if you have multiple TPUs, then you can see this go. So we'll talk a little bit about the JAX that's underneath here and the algorithm. This algorithm is very clever. I don't want to go into the pieces of it, but it is a very clever algorithm for the fast Fourier transform. And then we can actually run this. I'm almost done. So we'll let this run. It knows it has 8 TPU cores. The matrix that we're actually using is kind of small for 8 TPU cores. So our speed up is less impressive. This is strong scaling. So we're taking the same amount of work and dividing it up and dividing it up. If we do weak scaling and give it more work, then we'll see a bigger speed up than this. But if we compare again to 1 TPU or to 1 CPU, speed up is massive. So there's really a neat advantage to letting TPUs do what they do. There's some takeaways. Some of the things I linked in the presentation are here as well to kind of talk about documentation and do this. So this was a lot. A lot of times this is in a longer format, but I just wanted to give you an overview of how Google is thinking about TPUs, what we're working on. There's hands-on things for you to try. I would love for you to explore this as an option, and that's all I got. So thank you all.
Great. Thank you, John. Everybody, please give John a round of applause. And we will, there's a couple of questions already submitted, and I invite you to submit questions in the Q&A feature. Remember, you click on the icon next to the chat icon, and it's called Meeting Tools, and that pulls up a list of meeting tools, one of which is Q&A. So I see Bob Sorenson's on and asked exactly the question I would expect after seeing him mention that topic at the TPC 26 conference. Bob asks, how do these FP64 emulators adhere to the range of IEEE 754 64-bit FP standards? John, I'm sure you were just reading that this morning for breakfast.
Yeah,
that's standard.
So on my bedside table.
Yeah.
I think the short answer is that they don't. It is an EF, an emulated floating point 57. So that is the precision that you get from the emulated floating point. So it is a different standard. The implementation is out there on GitHub. I can, if you track me down, I can send you a link to that if you're interested. I don't have it on hand with me, but it is something that's out there, and it's not perfect, but it's pretty good.
All right. And Timur asks, are there analogous libraries to cuBLAS and cuFFT for TPUs?
Yeah, so there's actually a JAX FFT, and in the distributed FFT implementation, that's what we're using on each TPU. So each TPU does its local FFT, but the distribution piece is done, again, manually and very cleverly through these einsums, this all-to-all communication, this p-permute. There's a shuffle, and there's a butterfly step. If you're really into this, then you already know all this stuff. If you're not into this and curious, there are actually some really great YouTube videos that are out there that are extremely high quality. If you just look up fast Fourier transforms, you'll see some I could recommend. But so that one is in there. BLAS is not. So some libraries are already supported on TPUs. Some are missing, and they would have to be, implemented in some way or another, or, just kind of future work.
All right. I think we got another new question that just came in. Caleb asks, how do TPUs handle finite differences like eighth order? Can we control each thread individually like the GPU?
Those are two very different questions. I actually don't know what you mean on the eighth order finite differences. That swirl LM, well, that's a fluid dynamics code. Yeah, I don't know how to answer that one. As far as controlling each thread individually, we don't want to do that. So the idea of GPUs is the local cache is very important to the compute elements that you're using on a GPU. And typically in the programming model, you will launch multiple kernels, right? Each one gets a little slice of memory, and it runs that way. TPUs, you want the whole TPU active on your problem. So you're trying to map to at least the entire TPU. And if you're using multi-TPUs, you want to do all of it. So you're not controlling threads in the same way. Again, the way the systolic array is, they all kind of work with each other. So JAX does not support that. In fact, one of the reasons why Google loves JAX is because it's intended to use the whole device within one kernel. It takes the code, it does a just-in-time trace of everything. It lays out exactly how you're going to use the memory. It keeps everything double buffered and pushes it through the hardware.
Great. And Mike Carew says, low precision is great except for orthogonalization and factorization of ill-conditioned problems. Amdahl's law is operative here. Replacing only a fraction of high precision computations with low precision will only get you so much improvement. What is your experience of actual speed up?
That's a good question. Thus far, we have avoided using Ozaki's scheme to really look at the overhead. I agree with all this, and I've actually seen different implementations. I've seen people use the CPU for pieces that are high, precision, and then offload to the TPU. And some of those implementations actually get really good speedups because it turns out most of the math that's involved can be done in low precision. I think the real answer here will be algorithm dependent. We already see this when we've adopted GPUs from CPUs. There are some codes that remain CPU codes because they don't map well to GPU architecture. I think we're going to see a lot of HPC codes that map well to TPU architecture, but there will be some where this precision trade-off is just not quite a good fit. And I think that's okay.
Yeah, and I'll add a little bit to that, Mike. I think one of the viewpoints of the people that are in favor of this is not that you always have to get a tremendous speed up, but that you do not have to deploy a bifurcated system with CPU nodes for the things that are not fully accelerated in TPU or GPU nodes for those that aren't. If you can get this emulation working and at least get comparable performance, if not a huge speed up, on a system that is built mostly around these lower precision, higher performance accelerators, then you get your win on the applications that perform really well on them, and you don't lose on the applications that don't. So I think on the ones that require emulation, often the goal is just getting, comparable so that you can maintain one more homogeneous system design for the applications that benefit from it. So, but I think the jury is, still very, very, very out on that. We've seen Ozaki, we've seen Ozaki 2. We haven't seen Ozaki 3 and all the other things we'll probably see this year. I do want to refer you also, Mike, to a blog post that Substrate did on using mixed precision on TPUs and some interesting results they got. So you can Google search for that, but the company was called Substrate, and they did some really neat mixed precision work with TPUs. All right. I think that is the final question. So Mary, if you could pull up the final slides and we'll promote next week's talk. Let's give John another round of applause. Thank you, John.